Black body radiation is the type of electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment, or emitted by a black body held at constant, uniform temperature. The radiation has a specific spectrum and intensity that depends only on the temperature of the body. The thermal radiation spontaneously emitted by many ordinary objects can be approximated as blackbody radiation. A perfectly insulated enclosure that is in thermal equilibrium internally contains blackbody radiation and will emit it through a hole made in its wall, provided the hole is small enough to have negligible effect upon the equilibrium. A black body at room temperature appears black, as most of the energy it radiates is infrared and cannot be perceived by the human eye. Because the human eye cannot perceive color at very low light intensities, a black body, viewed in the dark at the lowest just faintly visible temperature, subjectively appears gray, even though its objective physical spectrum peaks in the infrared range. When it becomes a little hotter, it appears dull red. As its temperature increases further, it eventually becomes blindingly brilliant blue-white. Although planets and stars are neither in thermal equilibrium with their surroundings nor perfect black bodies, black body radiation is used as a first approximation for the energy they emit. Black holes are near-perfect black bodies, in the sense that they absorb all the radiation that falls on them. It has been proposed that they emit black body radiation, with a temperature that depends on the mass of the black hole. The term black body was introduced by Gustav Kirchhoff in 1860. When used as a compound adjective, the term is typically written as hyphenated, for example, black body radiation, but sometimes also as one word, as in black body radiation. Black body radiation is also called complete radiation, or temperature radiation, or thermal radiation. Spectrum. Black body radiation has a characteristic, continuous frequency spectrum that depends only on the body's temperature, called the Planck spectrum or Planck's law. The spectrum is peaked at a characteristic frequency that shifts to higher frequencies with increasing temperature, and at room temperature most of the emission is in the infrared region of the electromagnetic spectrum. As the temperature increases past about 500 degrees Celsius, black bodies start to emit significant amounts of visible light. Viewed in the dark, the first faint glow appears as of ghostly gray. With rising temperature, the glow becomes visible even when there is some background surrounding light. First as a dull red, then yellow, and eventually a dazzling bluish-white, as the temperature rises. When the body appears white, it is emitting a substantial fraction of its energy as ultraviolet radiation. The Sun, with an effective temperature of approximately 5,800 K, is an approximately black body with an emission spectrum peaked in the central, yellow-green part of the visible spectrum, but with significant power in the ultraviolet as well. Black body radiation provides insight into the thermodynamic equilibrium state of cavity radiation. If each Fourier mode of the equilibrium radiation in an otherwise empty cavity with perfectly reflective walls is considered as a degree of freedom, capable of exchanging energy, then, according to the equipartition theorem of classical physics, there would be an equal amount of energy in each mode. Since there are an infinite number of modes, this implies infinite heat capacity, as well as an unphysical spectrum of emitted radiation that grows without bound with increasing frequency, a problem known as the ultraviolet catastrophe. Instead, in quantum theory, the occupation numbers of the modes are quantized, cutting off the spectrum at high frequency in agreement with experimental observation and resolving the catastrophe. The study of the laws of black bodies and the failure of classical physics to describe them helped establish the foundations of quantum mechanics. Explanation. All normal matter emits electromagnetic radiation when it has a temperature above absolute zero. The radiation represents a conversion of a body's thermal energy into electromagnetic energy, and is therefore called thermal radiation. It is a spontaneous process of radiative distribution of entropy. Conversely, all normal matter absorbs electromagnetic radiation to some degree. An object that absorbs all radiation falling on it, at all wavelengths, is called a black body. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. Its emission is called black body radiation. The concept of the black body is an idealization, as perfect black bodies do not exist in nature. Graphite and lamp black, with emissivities greater than 0.95, however, are good approximations to a black material. Experimentally, black body radiation may be established best as the ultimately stable steady-state equilibrium radiation in a cavity in a rigid body. At a uniform temperature, that is entirely opaque and is only partly reflective. A closed box of graphite walls at a constant temperature with a small hole on one side produces a good approximation to ideal black body radiation, emanating from the opening. Black body radiation has the unique absolutely stable distribution of radiative intensity that can persist in thermodynamic equilibrium in a cavity. In equilibrium, for each frequency, the total intensity of radiation that is emitted and reflected from a body is determined solely by the equilibrium temperature, and does not depend upon the shape, material or structure of the body. For a black body there is no reflected radiation, and so the spectral radiance is due entirely to emission. In addition, a black body is a diffuse emitter. Consequently, black body radiation may be viewed as the radiation from a black body at thermal equilibrium. Black body radiation becomes a visible glow of light if the temperature of the object is high enough. The Draper point is the temperature at which all solids glow at dim red, about 798 K. At 1000 K, a small opening in the wall of a large uniformly heated opaque walled cavity, viewed from outside, looks red. At 6000 K, it looks white. No matter how the oven is constructed, or of what material, as long as it is built so that almost all light entering is absorbed by its walls, it will contain a good approximation to black body radiation. The spectrum, and therefore color, of the light that comes out will be a function of the cavity temperature alone. A graph of the amount of energy inside the oven per unit volume and per unit frequency interval plotted versus frequency is called the black body curve. Different curves are obtained by varying the temperature. Two bodies that are at the same temperature stay in mutual thermal equilibrium. So a body at temperature T surrounded by a cloud of light at temperature T on average will emit as much light into the cloud as it absorbs. Following Prevost's exchange principle, which refers to radiative equilibrium, the principle of detailed balance says that in thermodynamic equilibrium every elementary process works equally in its forward and backward sense. Prevost also showed that the emission from a body is logically determined solely by its own internal state. The causal effect of thermodynamic absorption on thermodynamic emission is not direct, but is only indirect as it affects the internal state of the body. This means that at thermodynamic equilibrium, the amount of every wavelength and every direction of thermal radiation emitted by a body at temperature T, black or not, is equal to the corresponding amount that the body absorbs because it is surrounded by light at temperature T. When the body is black, the absorption is obvious. The amount of light absorbed is all the light that hits the surface. For a black body much bigger than the wavelength, the light energy absorbed at any wavelength lambda per unit time is strictly proportional to the black body curve. This means that the black body curve is the amount of light energy emitted by a black body, which justifies the name. This is the condition for the applicability of Kirchhoff's law of thermal radiation. The black body curve is characteristic of thermal light, which depends only on the temperature of the walls of the cavity, provided that the walls of the cavity are completely opaque and are not very reflective, and that the cavity is in thermodynamic equilibrium. When the black body is small, so that its size is comparable to the wavelength of light, the absorption is modified. Because a small object is not an efficient absorber of light of long wavelength, But the principle of strict equality of emission and absorption is always upheld in a condition of thermodynamic equilibrium. In the laboratory, black body radiation is approximated by the radiation from a small hole in a large cavity, a hole ram, in an entirely opaque body that is only partly reflective, that is maintained at a constant temperature. Any light entering the hole would have to reflect off the walls of the cavity multiple times before it escaped, in which process it is nearly certain to be absorbed. Absorption occurs regardless of the wavelength of the radiation entering. The hole, then, is a close approximation of a theoretical black body, and, if the cavity is heated, the spectrum of the hole's radiation will be continuous, and will depend only on the temperature and the fact that the walls are opaque and at least partly absorptive, but not on the particular material of which they are built nor on the material in the cavity. Calculating the black body curve was a major challenge in theoretical physics during the late 19th century. The problem was solved in 1901 by Max Planck in the formalism now known as Planck's law of black body radiation. By making changes to Wien's radiation law, consistent with thermodynamics and electromagnetism, he found a mathematical expression fitting the experimental data satisfactorily. Planck had to assume that the energy of the oscillators in the cavity was quantized, i.e., it existed in integer multiples of some quantity. Einstein built on this idea and proposed the quantization of electromagnetic radiation itself in 1905 to explain the photoelectric effect. These theoretical advances eventually resulted in the superseding of classical electromagnetism by quantum electrodynamics. These quanta were called photons, and the black body cavity was thought of as containing a gas of photons. In addition, it led to the development of quantum probability distributions, called Fermi-Dirac statistics and Bose-Einstein statistics, each applicable to a different class of particles, fermions and bosons. The wavelength at which the radiation is strongest is given by Wien's displacement law, and the overall power emitted per unit area is given by the Stefan-Boltzmann law. So, as temperature increases, the glow color changes from red to yellow to white to blue. Even as the peak wavelength moves into the ultraviolet, enough radiation continues to be emitted in the blue wavelengths that the body will continue to appear blue. It will never become invisible. Indeed, the radiation of visible light increases monotonically with temperature. The radiance or observed intensity is not a function of direction. Therefore, a black body is a perfect Lambertian radiator. Real objects never behave as full ideal black bodies, and instead the emitted radiation at a given frequency is a fraction of what the ideal emission would be. The emissivity of immaterial specifies how well a real body radiates energy as compared with a black body. This emissivity depends on factors such as temperature, emission angle, and wavelength. However, it is typical in engineering to assume that a surface's spectral emissivity and absorptivity do not depend on wavelength, so that the emissivity is a constant. This is known as the gray body assumption. With non-black surfaces, the deviations from ideal black body behavior are determined by both the surface structure, such as roughness or granularity, and the chemical composition. On a per-wavelength basis, real objects in states of local thermodynamic equilibrium still follow Kirchhoff's law. Emissivity equals absorptivity, so that an object that does not absorb all incident light will also emit less radiation than an ideal black body. The incomplete absorption can be due to some of the incident light being transmitted through the body or to some of it being reflected at the surface of the body. In astronomy, objects such as stars are frequently regarded as black bodies, though this is often a poor approximation. An almost perfect black body spectrum is exhibited by the cosmic microwave background radiation. Hawking radiation is the hypothetical black body radiation emitted by black holes, at a temperature that depends on the mass, charge, and spin of the hole. If this prediction is correct, Black holes will very gradually shrink and evaporate over time as they lose mass by the emission of photons and other particles. A black body radiates energy at all frequencies, but its intensity rapidly tends to zero at high frequencies. For example, a black body at room temperature with 1 square meter of surface area will emit a photon in the visible range at an average rate of 1 photon every 41 seconds. Meaning that for most practical purposes, such a black body does not emit in the visible range. Equations. Planck's law of black body radiation. Planck's law states that where I is the energy per unit time radiated per unit area of emitting surface in the normal direction per unit solid angle per unit frequency by a black body at temperature T, also known as spectral radiance. H is the Planck constant, C is the speed of light in a vacuum, K is the Boltzmann constant, nu is the frequency of the electromagnetic radiation, and T is the absolute temperature of the body. Wien's displacement law. Wien's displacement law shows how the spectrum of black body radiation at any temperature is related to the spectrum at any other temperature. If we know the shape of the spectrum at one temperature, we can calculate the shape at any other temperature. Spectral intensity can be expressed as a function of wavelength or of frequency. A consequence of Wien's displacement law is that the wavelength at which the intensity per unit wavelength of the radiation produced by a black body is at a maximum, is a function only of the temperature where the constant, B, known as Wien's displacement constant, is equal to 2.89772897772000000002.89777721 times 10⁻³ km. Planck's law was also stated above as a function of frequency. The intensity maximum for this is given by Stefan-Boltzmann law. The Stefan-Boltzmann law states that the power emitted per unit area of the surface of a black body is directly proportional to the fourth power of its absolute temperature, where J* is the total power radiated per unit area, T is the absolute temperature, and sigma equals 69925670000000005.67 times 10⁻8 Wm-2 K-4 is the Stefan-Boltzmann constant. This follows from integrating over frequency and solid angle. The factor appears since we are considering the radiation in the direction normal to the surface. The solid angle integral extends over the full in azimuth, and over half the domain of polar angle, is independent of angles and passes through the solid angle integral. Inserting the formula for gives us unitless. The integral over has the value, which gives human body emission. As all matter, the human body radiates some of a person's energy away as infrared light. The net power radiated is the difference between the power emitted and the power absorbed. Applying the Stefan-Boltzmann law, the total surface area of an adult is about 2 square meters, and the mid and far infrared emissivity of skin and most clothing is near unity, as it is for most non-metallic surfaces. Skin temperature is about 33 degrees Celsius, but clothing reduces the surface temperature to about 28 degrees Celsius when the ambient temperature is 20 degrees Celsius. Hence, the net radiative heat loss is about the total energy radiated in one day is about 9 megajoules, or 2000 kilocalories. Basal metabolic rate for a 40-year-old male is about 35 kilocalories, which is equivalent to 1,700 kilocalories per day assuming the same 2 square meters area. However, the mean metabolic rate of sedentary adults is about 50% to 70% greater than their basal rate. There are other important thermal loss mechanisms, including convection and evaporation. Conduction is negligible, the Nusselt number is much greater than unity. Evaporation via perspiration is only required if radiation and convection are insufficient to maintain a steady state temperature. Free convection rates are comparable, albeit somewhat lower, than radiative rates. Thus, radiation accounts for about two-thirds of thermal energy loss in cool, still air. Given the approximate nature of many of the assumptions, this can only be taken as a crude estimate. Ambient air motion, causing forced convection, or evaporation reduces the relative importance of radiation as a thermal loss mechanism. Application of Wien's law to human body emission results in a peak wavelength of. For this reason, thermal imaging devices for human subjects are most sensitive in the 7 to 14 micron range.